Chapter 16. Navigation. This chapter provides an introduction to cross-country flying under Visual Flight Rules, VFR. It contains practical information for planning and executing cross-country flights for the beginning pilot. Air navigation is the process of piloting an aircraft from one geographic position to another while monitoring one's position as the flight progresses. It introduces the need for planning, which includes plotting the course on an aeronautical chart, selecting checkpoints, measuring distances, obtaining pertinent weather information, and computing flight time, headings, and fuel requirements. The methods used in this chapter include pilotage, navigating by reference to visible landmarks, dead reckoning, computations of direction and distance from a known position, and radio navigation, by use of radio aids. Aeronautical charts. An aeronautical chart is the roadmap for a pilot flying under VFR. The chart provides information that allows pilots to track their position and provides available information that enhances safety. The three aeronautical charts used by VFR pilots are sectional, VFR terminal area, World Aeronautical. A free catalog listing aeronautical charts and related publications including prices and instructions for ordering is available at the Aeronautical Navigation Products website, www.aeronav.faa.gov. Sectional charts. Sectional charts are the most common charts used by pilots today. The charts have a scale of 1 to 500,000, 1 inch equals 6.86 nautical miles, nm, or approximately 8 statute miles, sm, which allows for more detailed information to be included on the chart. The charts provide an abundance of information, including airport data, navigational aids, airspace, and topography. Figure 16:1 is an excerpt from the legend of a sectional chart. By referring to the chart legend, a pilot can interpret most of the information on the chart. A pilot should also check the chart for other legend information, which includes air traffic control, ATC, frequencies and information on airspace. These charts are revised semi-annually except for some areas outside the conterminous United States where they are revised annually. VFR Terminal Area Charts. VFR Terminal Area Charts are helpful when flying in or near Class B airspace. They have a scale of 1 to 250,000, 1 inch equals 3.43 nanometer or approximately 4 sm. These charts provide a more detailed display of topographical information and are revised semi-annually, except for several Alaskan and Caribbean charts. World Aeronautical Charts. World Aeronautical Charts are designed to provide a standard series of aeronautical charts, covering land areas of the world, at a size and scale convenient for navigation by moderate-speed aircraft. They are produced at a scale of 1 to 1 million, 1 inch equals 13.7 nanometer or approximately 16 sm. These charts are similar to sectional charts, and the symbols are the same except there is less detail due to the smaller scale. Figure 16:3. These charts are revised annually except several Alaskan charts and the Mexican, Caribbean charts, which are revised every 2 years. Latitude and longitude, meridians and parallels. The equator is an imaginary circle equidistant from the poles of the Earth. Circles parallel to the equator, lines running east and west, are parallels of latitude. They are used to measure degrees of latitude north, n, or south, s, of the equator. The angular distance from the equator to the pole is 1/4 of a circle or 90 degrees. The 48 conterminous states of the United States are located between 25 degrees and 49 degrees north latitude. The arrows in Figure 16:4 labeled latitude point to lines of latitude. Meridians of longitude are drawn from the North Pole to the South Pole and are at right angles to the equator. The prime meridian, which passes through Greenwich, England, is used as the zero line from which measurements are made in degrees east, E, and west, W, to 180 degrees. The 48 conterminous states of the United States are between 67 degrees and 125 degrees west longitude. The arrows in Figure 16-4 labeled longitude point to lines of longitude. Any specific geographical point can be located by reference to its longitude and latitude. Washington, D.C., for example, is approximately 39 degrees north latitude, 77 degrees west longitude. Chicago is approximately 42 degrees north latitude, 88 degrees west longitude. Time zones. The meridians are also useful for designating time zones. A day is defined as the time required for the Earth to make one complete rotation of 360 degrees. Since the day is divided into 24 hours, the Earth revolves at the rate of 15 degrees an hour. Noon is the time when the sun is directly above a meridian. To the west of that meridian is morning, to the east is afternoon. The standard practice is to establish a time zone for each 15 degrees of longitude. This makes a difference of exactly 1 hour between each zone. In the conterminous United States, there are 4 time zones. The time zones are Eastern, 75 degrees, Central, 90 degrees, Mountain, 105 degrees, and Pacific, 120 degrees. The dividing lines are somewhat irregular because communities near the boundaries often find it more convenient to use time designations of neighboring communities or trade centers. Figure 16-5 shows the time zones in the conterminous United States. When the sun is directly above the 90th meridian, it is noon Central Standard Time. At the same time, it is 1 p.m. Eastern Standard Time, 11 a.m. Mountain Standard Time, and 10 a.m. Pacific Standard Time. When daylight saving time is in effect, generally between the second Sunday in March and the first Sunday in November, the sun is directly above the 75th meridian at noon, Central Daylight Time. These time zone differences must be taken into account during long flights eastward, especially if the flight must be completed before dark. Remember, an hour is lost when flying eastward from one time zone to another, or perhaps even when flying from the western edge to the eastern edge of the same time zone. Determine the time of sunset at the destination by consulting the Flight Service Station, FSS, and take this into account when planning an eastbound flight. In most aviation operations, time is expressed in terms of the 24-hour clock. ATC instructions, weather reports and broadcasts, and estimated times of arrival are all based on this system. For example, 9 a.m. is expressed as 0900, 1 p.m. is 1300, and 10 p.m. is 2200. Because a pilot may cross several time zones during a flight, a standard time system has been adopted. It is called Universal Coordinated Time, UTC, and is often referred to as Zulu time. UTC is the time at the 0 degrees line of longitude which passes through Greenwich, England. All of the time zones around the world are based on this reference. To convert to this time, a pilot should do the following. Eastern Standard Time, add 5 hours. Central Standard Time, add 6 hours. Mountain Standard Time, add 7 hours. Pacific Standard Time, add 8 hours. For daylight saving time, 1 hour should be subtracted from the calculated times. Measurement of direction. By using the meridians, direction from one point to another can be measured in degrees, in a clockwise direction from true north. To indicate a course to be followed in flight, draw a line on the chart from the point of departure to the destination and measure the angle that this line forms with a meridian. Direction is expressed in degrees, as shown by the compass rose in Figure 16-6. Because meridians converge toward the poles, course measurement should be taken at a meridian near the midpoint of the course rather than at the point of departure. The course measured on the chart is known as the true course, TC. This is the direction measured by reference to a meridian or true north, TN. It is the direction of intended flight as measured in degrees clockwise from TN. As shown in figure 16-7, the direction from A to B would be a TC of 065 degree, whereas the return trip, called the reciprocal, would be a TC of 245 degrees. The true heading, TH, is the direction in which the nose of the aircraft points during a flight when measured in degrees clockwise from TN. Usually, it is necessary to head the aircraft in a direction slightly different from the TC to offset the effect of wind. Consequently, numerical value of the TH may not correspond with that of the TC. This is discussed more fully in subsequent sections in this chapter. For the purpose of this discussion, assume a no-wind condition exists under which heading and course would coincide. Thus, for a TC of 065 degree, the TH would be 065 degree. To use the compass accurately, however, corrections must be made for magnetic variation and compass deviation. Variation. Variation is the angle between Tn and magnetic north, Mn. It is expressed as east variation or west variation depending upon whether Mn is to the east or west of Tn. The north magnetic pole is located close to 71 degrees north latitude, 96 degrees west longitude, and is about 1,300 miles from the geographic or true North Pole, as indicated in figure 16-8. If the Earth were uniformly magnetized, the compass needle would point toward the magnetic pole, in which case the variation between Tn, as shown by the geographical meridians, and Mn, as shown by the magnetic meridians, could be measured at any intersection of the meridians. Actually, the Earth is not uniformly magnetized. In the United States, the needle usually points in the general direction of the magnetic pole, but it may vary in certain geographical localities by many degrees. Consequently, the exact amount of variation at thousands of selected locations in the United States has been carefully determined. The amount and the direction of variation, which change slightly from time to time, are shown on most aeronautical charts as broken magenta lines called isogonic lines that connect points of equal magnetic variation. The line connecting points at which there is no variation between Tn and Mn is the agonic line. An isogonic chart is shown in figure 16-9. Minor bends and turns in the isogonic and agonic lines are caused by unusual geological conditions affecting magnetic forces in these areas. On the west coast of the United States, the compass needle points to the east of Tn. On the east coast, the compass needle points to the west of Tn. 0-degree variation exists on the agonic line where Mn and Tn coincide. This line runs roughly west of the Great Lakes, south through Wisconsin, Illinois, western Tennessee, and along the border of Mississippi and Alabama. Compare figures 16-9 and 16-10. Because courses are measured in reference to geographical meridians that point toward Tn, and these courses are maintained by reference to the compass that points along a magnetic meridian in the general direction of Mn, the true direction must be converted into magnetic direction for the purpose of flight. This conversion is made by adding or subtracting the variation indicated by the nearest isogonic line on the chart. For example, a line drawn between 2 points on a chart is called a TC as it is measured from Tn. However, flying this course off the magnetic compass would not provide an accurate course between the 2 points due to 3 elements that must be considered. The first is magnetic variation, the second is compass deviation, and the third is wind correction. All 3 must be considered for accurate navigation. Magnetic variation. As mentioned in the paragraph discussing variation, the appropriate variation for the geographical location of the flight must be considered and added or subtracted as appropriate. If flying across an area where the variation changes, then the values must be applied along the route of flight appropriately. Once applied, this new course is called the magnetic course. Magnetic deviation. Because each aircraft has its own internal effect upon the onboard compass systems from its own localized magnetic influences, the pilot must add or subtract these influences based upon the direction he or she is flying. The application of deviation, taken from a compass deviation card, compensates the magnetic course unique to that aircraft's compass system, as affected by localized magnetic influences, and it now becomes the compass course. Therefore, the compass course, when followed, in a no-wind condition, takes the aircraft from point A to point B even though the aircraft heading may not match the original course line drawn on the chart. If the variation is shown as 9 degrees east, this means that MN is 9 degrees east of TN. If a TC of 360 degrees is to be flown, 9 degrees must be subtracted from 360 degrees, which results in a magnetic heading of 351 degrees. To fly east, a magnetic course of 081 degree, 090 degree 9 degrees, would be flown. To fly south, the magnetic course would be 171 degrees, 180 degrees to 9 degrees. To fly west, it would be 261 degrees, 270 degrees to 9 degrees. To fly a TH of 060 degree, a magnetic course of 051 degree, 060 degree 9 degrees, would be flown. Remember, if variation is west, add; if east, subtract. One method for remembering whether to add or subtract variation is the phrase, east is least, subtract, and west is best, add. Deviation. Determining the magnetic heading is an intermediate step necessary to obtain the correct compass heading for the flight. To determine compass heading, a correction for deviation must be made. Because of magnetic influences within an aircraft, such as electrical circuits, radio, lights, tools, engine, and magnetized metal parts, the compass needle is frequently deflected from its normal reading. This deflection is called deviation. The deviation is different for each aircraft, and it also may vary for different headings in the same aircraft. For instance, if magnetism in the engine attracts the north end of the compass, there would be no effect when the plane is on a heading of MN. On easterly or westerly headings, however, the compass indications would be in error, as shown in Figure 16 to 11. Magnetic attraction can come from many other parts of the aircraft. The assumption of attraction in the engine is merely used for the purpose of illustration. Some adjustment of the compass, referred to as compensation, can be made to reduce this error, but the remaining correction must be applied by the pilot. Proper compensation of the compass is best performed by a competent technician. Since the magnetic forces within the aircraft change because of landing shocks, vibration, mechanical work, or changes in equipment, the pilot should occasionally have the deviation of the compass checked. The procedure used to check the deviation is called swinging the compass, and is briefly outlined as follows. The aircraft is placed on a magnetic compass rose, the engine started, and electrical devices normally used, such as radio, are turned on. Tailwheel type aircraft should be jacked up into flying position. The aircraft is aligned with MN indicated on the compass rose, and the reading shown on the compass is recorded on a deviation card. The aircraft is then aligned at 30 degrees intervals, and each reading is recorded. If the aircraft is to be flown at night, the lights are turned on and any significant changes in the readings are noted. If so, additional entries are made for use at night. The accuracy of the compass can also be checked by comparing the compass reading with the known runway headings. A deviation card, similar to Figure 16 to 12, is mounted near the compass showing the addition or subtraction required to correct for deviation on various headings, usually at intervals of 30 degrees. For intermediate readings, the pilot should be able to interpolate mentally with sufficient accuracy. For example, if the pilot needed the correction for 195 degrees and noted the correction for 180 degrees to be 0 degrees and for 210 degrees to be +2 degrees, it could be assumed that the correction for 195 degrees would be plus 1 degree. The magnetic heading, when corrected for deviation, is known as compass heading. Effect of wind. The preceding discussion explained how to measure a TC on the aeronautical chart and how to make corrections for variation and deviation, but one important factor has not been considered: wind. As discussed in the study of the atmosphere, wind is a mass of air moving over the surface of the Earth in a definite direction. When the wind is blowing from the north at 25 knots, it simply means that air is moving southward over the Earth's surface at the rate of 25 nanometer in 1 hour. Under these conditions, any inert object free from contact with the Earth is carried 25 nanometers southward in 1 hour. This effect becomes apparent when such things as clouds, dust, and toy balloons are observed being blown along by the wind. Obviously, an aircraft flying within the moving mass of air is similarly affected. Even though the aircraft does not float freely with the wind, it moves through the air at the same time the air is moving over the ground, and thus is affected by wind. Consequently, at the end of 1 hour of flight, the aircraft is in a position that results from a combination of the following two motions. Movement of the air mass in reference to the ground. Forward movement of the aircraft through the air mass. Actually, these two motions are independent. It makes no difference whether the mass of air through which the aircraft is flying is moving or is stationary. A pilot flying in a 70-knot gale would be totally unaware of any wind, except for possible turbulence, unless the ground were observed. In reference to the ground, however, the aircraft would appear to fly faster with a tailwind or slower with a headwind, or to drift right or left with a crosswind. As shown in figures 16 to 13, an aircraft flying eastward at an airspeed of 120 knots in still air has a ground speed, GS, exactly the same, 120 knots. If the mass of air is moving eastward at 20 knots, the airspeed of the aircraft is not affected, but the progress of the aircraft over the ground is 120 plus 20 or a GS of 140 knots. On the other hand, if the mass of air is moving westward at 20 knots, the airspeed of the aircraft remains the same, but GS becomes 120 minus 20 or 100 knots. Assuming no correction is made for wind effect, if an aircraft is heading eastward at 120 knots and the air mass moving southward at 20 knots, the aircraft at the end of 1 hour is almost 120 miles east of its point of departure because of its progress through the air. It is 20 miles south because of the motion of the air. Under these circumstances, the airspeed remains 120 knots, but the GS is determined by combining the movement of the aircraft with that of the air mass. GS can be measured as the distance from the point of departure to the position of the aircraft at the end of 1 hour. The GS can be computed by the time required to fly between 2 points a known distance apart. It also can be determined before flight by constructing a wind triangle, which is explained later in this chapter. The direction in which the aircraft is pointing as it flies is called heading. Its actual path over the ground, which is a combination of the motion of the aircraft and the motion of the air, is called track. The angle between the heading and the track is called drift angle. If the aircraft heading coincides with the TC and the wind is blowing from the left, the track does not coincide with the TC. The wind causes the aircraft to drift to the right, so the track falls to the right of the desired course or TC. The following method is used by many pilots to determine compass heading, after the TC is measured and wind correction applied resulting in a TH, the sequence TH plus or minus variation, V, equals magnetic heading, MH, plus or minus deviation, D, equals compass heading, CH, is followed to arrive at compass heading. By determining the amount of drift, the pilot can counteract the effect of the wind and make the track of the aircraft coincide with the desired course. If the mass of air is moving across the course from the left, the aircraft drifts to the right, and a correction must be made by heading the aircraft sufficiently to the left to offset this drift. In other words, if the wind is from the left, the correction is made by pointing the aircraft to the left a certain number of degrees, therefore correcting for wind drift. This is the wind correction angle, WCA, and is expressed in terms of degrees right or left of the TC. To summarize: course, intended path of an aircraft over the ground or the direction of a line drawn on a chart representing the intended aircraft path, expressed as the angle measured from a specific reference datum clockwise from 0 degrees through 360 degrees to the line. Heading, direction in which the nose of the aircraft points during flight. Track, actual path made over the ground in flight. If proper correction has been made for the wind, track and course are identical. Drift angle, angle between heading and track. WCA, correction applied to the course to establish a heading so that track coincides with course. Airspeed, rate of the aircraft's progress through the air. GS, rate of the aircraft's in-flight progress over the ground. Basic calculations. Before a cross-country flight, a pilot should make common calculations for time, speed, and distance, and the amount of fuel required. Converting minutes to equivalent hours. Frequently, it is necessary to convert minutes into equivalent hours when solving speed, time, and distance problems. To convert minutes to hours, divide by 60, 60 minutes equals 1 hour. Thus, 30 minutes is 30 divided by 60 equals 0.5 hour. To convert hours to minutes, multiply by 60. Thus, 0.75 hour equals 0.75 times 60 equals 45 minutes. Time t equals d, gs. To find the time, t, in flight, divide the distance, d, by the gs. The time to fly 210 nanometer at a gs of 140 knots is 210 divided by 140 or 1.5 hours. The 0.5 hour multiplied by 60 minutes equals 30 minutes. Answer: 130. Distance d equals gs/t. To find the distance flown in a given time, multiply gs by time. The distance flown in 1 hour 45 minutes at a gs of 120 knots is 120 times 1.75 or 210 nanometer. gs equals d, t. To find the gs, divide the distance flown by the time required. If an aircraft flies 270 nanometer in 3 hours, the gs is 270 divided by 3 equals 90 knots. Converting knots to miles per hour. Another conversion is that of changing knots to miles per hour, mph. The aviation industry is using knots more frequently than mph, but is important to understand the conversion for those that use mph when working with speed problems. The NWS reports both surface winds and winds aloft in knots. However, airspeed indicators in some aircraft are calibrated in mph, although many are now calibrated in both mph and knots. Pilots, therefore, should learn to convert wind speeds that are reported in knots to mph. A knot is 1 nautical mile per hour, nmph. Because there are 6,076.1 feet in 1 nanometer and 5,280 feet in 1 sm, the conversion factor is 1.15. To convert knots to mph, multiply speed in knots by 1.15. For example, a wind speed of 20 knots is equivalent to 23 miles per hour. Most flight computers or electronic calculators have a means of making this conversion. Another quick method of conversion is to use the scales of nanometer and sm at the bottom of aeronautical charts. Fuel consumption. To ensure that sufficient fuel is available for your intended flight, you must be able to accurately compute aircraft fuel consumption during pre-flight planning. Typically, fuel consumption in gasoline-fueled aircraft is measured in gallons per hour. Since turbine engines consume much more fuel than reciprocating engines, turbine-powered aircraft require much more fuel, and thus much larger fuel tanks. When determining these large fuel quantities, using a volume measurement such as gallons presents a problem because the volume of fuel varies greatly in relation to temperature. In contrast, density, weight, is less affected by temperature and therefore provides a more uniform and repeatable measurement. For this reason, jet fuel is generally quantified by its density and volume. This standard industry convention yields a pounds of fuel per hour value which, when divided into the nautical miles, nm, per hour of travel, tas plus or minus winds, value, results in a specific range value. The typical label for specific range is nanometer per pound of fuel, or often nanometer per 1,000 pounds of fuel. Pre-flight planning should be supported by proper monitoring of past fuel consumption as well as use of specified fuel management and mixture adjustment procedures in flight. For simple aircraft with reciprocating engines, the Aircraft Flight Manual, Pilot's Operating Handbook, AFM, PO, supplied by the aircraft manufacturer provides gallons per hour values to assist with pre-flight planning. When planning a flight, you must determine how much fuel is needed to reach your destination by calculating the distance the aircraft can travel, with winds considered, at a known rate of fuel consumption, gallon per hour or pound per hour, for the expected ground speed, GS, and ensure this amount, plus an adequate reserve, is available on board. GS determines the time the flight will take. The amount of fuel needed for a given flight can be calculated by multiplying the estimated flight time by the rate of consumption. For example, a flight of 400 nanometer at 100 knots GS takes 4 hours to complete. If an aircraft consumes 5 gallons of fuel per hour, the total fuel consumption is 20 gallons, 4 hours times 5 gallons. In this example, there is no wind. Therefore, true airspeed, TAS, is also 100 knots, the same as GS. Since the rate of fuel consumption remains relatively constant at a given TAS, you must use GS to calculate fuel consumption when wind is present. Specific range, nanometer per pound or nanometer per gallon, is also useful in calculating fuel consumption when wind is a factor. You should always plan to be on the surface before any of the following occur. Your flight time exceeds the amount of flight time you calculated for the consumption of your pre-flight fuel amount. Your fuel gauge indicates low fuel level. The rate of fuel consumption depends on many factors: condition of the engine, propeller, rotor pitch, propeller, rotor revolutions per minute, RPM, richness of the mixture, and the percentage of horsepower used for flight at cruising speed. The pilot should know the approximate consumption rate from cruise performance charts or from experience. In addition to the amount of fuel required for the flight, there should be sufficient fuel for reserve. When estimating consumption, you must plan for cruise flight as well as startup and taxi, and higher fuel burn during climb. Remember that ground speed during climb is less than during cruise flight at the same airspeed. Additional fuel for adequate reserve should also be added as a safety measure. Flight computers. Up to this point, only mathematical formulas have been used to determine such items as time, distance, speed, and fuel consumption. In reality, most pilots use a mechanical flight computer called an E6B or electronic flight calculator. These devices can compute numerous problems associated with flight planning and navigation. The mechanical or electronic computer has an instruction book that probably includes sample problems so the pilot can become familiar with its functions and operation. Plotter. Another aid in flight planning is a plotter, which is a protractor and ruler. The pilot can use this when determining TC and measuring distance. Most plotters have a ruler that measures in both nanometer and SM and has a scale for a sectional chart on one side and a world aeronautical chart on the other. Pilotage. Pilotage is navigation by reference to landmarks or checkpoints. It is a method of navigation that can be used on any course that has adequate checkpoints, but it is more commonly used in conjunction with dead reckoning and VFR radio navigation. The checkpoints selected should be prominent features common to the area of the flight. Choose checkpoints that can be readily identified by other features, such as roads, rivers, railroad tracks, lakes, and power lines. If possible, select features that make useful boundaries or brackets on each side of the course, such as highways, rivers, railroads, and mountains. A pilot can keep from drifting too far off course by referring to and not crossing the selected brackets. Never place complete reliance on any single checkpoint. Choose ample checkpoints. If one is missed, look for the next one while maintaining the heading. When determining position from checkpoints, remember that the scale of a sectional chart is 1 inch equals 8 sm or 6.86 nanometer. For example, if a checkpoint selected was approximately 1/2 inch from the course line on the chart, it is 4 sm or 3.43 nanometer from the course on the ground. In the more congested areas, some of the smaller features are not included on the chart. If confused, hold the heading. If a turn is made away from the heading, it is easy to become lost. Roads shown on the chart are primarily the well-traveled roads or those most apparent when viewed from the air. New roads and structures are constantly being built and may not be shown on the chart until the next chart is issued. Some structures, such as antennas, may be difficult to see. Sometimes TV antennas are grouped together in an area near a town. They are supported by almost invisible guy wires. Never approach an area of antennas less than 500 feet above the tallest one. Most of the taller structures are marked with strobe lights to make them more visible to pilots. However, some weather conditions or background lighting may make them difficult to see. Aeronautical charts display the best information available at the time of printing, but a pilot should be cautious for new structures or changes that have occurred since the chart was printed. Dead reckoning. Dead reckoning is navigation solely by means of computations based on time, airspeed, distance, and direction. The products derived from these variables, when adjusted by wind speed and velocity, are heading and GS. The predicted heading takes the aircraft along the intended path and the GS establishes the time to arrive at each checkpoint and the destination. Except for flights over water, dead reckoning is usually used with pilotage for cross-country flying. The heading and GS, as calculated, is constantly monitored and corrected by pilotage as observed from checkpoints. Wind triangle or vector analysis. If there is no wind, the aircraft's ground track is the same as the heading and the GS is the same as the true airspeed. This condition rarely exists. A wind triangle, the pilot's version of vector analysis, is the basis of dead reckoning. The wind triangle is a graphic explanation of the effect of wind upon flight. GS, heading, and time for any flight can be determined by using the wind triangle. It can be applied to the simplest kind of cross-country flight, as well as the most complicated instrument flight. The experienced pilot becomes so familiar with the fundamental principles that estimates can be made that are adequate for visual flight without actually drawing the diagrams. The beginning student, however, needs to develop skill in constructing these diagrams as an aid to the complete understanding of wind effect. Either consciously or unconsciously, every good pilot thinks of the flight in terms of wind triangle. If flight is to be made on a course to the east, with a wind blowing from the northeast, the aircraft must be headed somewhat to the north of east to counteract drift. This can be represented by a diagram as shown in figure 16 to 19. Each line represents direction and speed. The long blue and white hashed line shows the direction the aircraft is heading, and its length represents the distance traveled at the indicated airspeed for 1 hour. The short blue arrow at the right shows the wind direction, and its length represents the wind velocity for 1 hour. The solid yellow line shows the direction of the track or the path of the aircraft as measured over the Earth, and its length represents the distance traveled in 1 hour or the GS. In actual practice, the triangle illustrated in figures 16 to 19 is not drawn. Instead, construct a similar triangle as shown by the blue, yellow, and black lines in figures 16 to 20, which is explained in the following example. Suppose a flight is to be flown from E to P. Draw a line on the aeronautical chart connecting these 2 points. Measure its direction with a protractor, or plotter, in reference to a meridian. This is the TC, which in this example is assumed to be 090 degree, east. From the NWS, it is learned that the wind at the altitude of the intended flight is 40 knots from the northeast, 045 degree. Since the NWS reports the wind speed in knots, if the true airspeed of the aircraft is 120 knots, there is no need to convert speeds from knots to mph or vice versa. Now, on a plain sheet of paper, draw a vertical line representing north to south. The various steps are shown in figure 16 to 21. Step 1. Place the protractor with the base resting on the vertical line and the curved edge facing east. At the center point of the base, make a dot labeled E, point of departure, and at the curved edge, make a dot at 90 degrees, indicating the direction of the true course, and another at 45 degrees, indicating wind direction. Step 2. With the ruler, draw the true course line from E, extending it somewhat beyond the dot by 90 degrees, and labeling it TC090 degree. Step 3. Next, align the ruler with E and the dot at 45 degrees, and draw the wind arrow from E, not toward 045 degree, but downwind in the direction the wind is blowing, making it 40 units long to correspond with the wind velocity of 40 knots. Identify this line as the wind line by placing the letter W at the end to show the wind direction. Step 4. Finally, measure 120 units on the ruler to represent the airspeed, making a dot on the ruler at this point. The units used may be of any convenient scale or value, such as 1/4 inch equals 10 knots, but once selected, the same scale must be used for each of the linear movements involved. Then place the ruler so that the end is on the arrowhead, W, and the 120 knot dot intercepts the TC line. Draw the line and label it as 120. The point, P, placed at the intersection represents the position of the aircraft at the end of 1 hour. The diagram is now complete. The distance flown in 1 hour, GS, is measured as the numbers of units on the TC line, 88 nautical miles per hour or 88 knots. The TH necessary to offset drift is indicated by the direction of the airspeed line, which can be determined in one of 2 ways. By placing the straight side of the protractor along the north-south line, with its center point at the intersection of the airspeed line and north-south line, read the TH directly in degrees, 076 degree. By placing the straight side of the protractor along the TC line, with its center at P, read the angle between the TC and the airspeed line. This is the WCA, which must be applied to the TC to obtain the TH. If the wind blows from the right of TC, the angle is added. If from the left, it is subtracted. In the example given, the WCA is 14 degrees and the wind is from the left. Therefore, subtract 14 degrees from TC of 090 degree, making the TH 076 degree. After obtaining the TH, apply the correction for magnetic variation to obtain magnetic heading and the correction for compass deviation to obtain a compass heading. The compass heading can be used to fly to the destination by dead reckoning. To determine the time and fuel required for the flight, first find the distance to your destination by measuring the length of the course line drawn on the aeronautical chart, using the appropriate scale at the bottom of the chart. If the distance measures 220 nanometer, divide by the GS of 88 knots, which gives 2.5 hours, or 2 to 30, as the time required. If fuel consumption is 8 gallons an hour, 8 times 2.5 or about 20 gallons is used. Briefly summarized, the steps in obtaining flight information are as follows. TC, direction of the line connecting two desired points, drawn on the chart and measured clockwise in degrees from TN on the mid-meridian. WCA, determined from the wind triangle. Added to TC if the wind is from the right, subtracted if wind is from the left. TH, direction measured in degrees clockwise from TN, in which the nose of the plane should point to remain on the desired course. Variation, obtained from the isogonic line on the chart, added to TH if west, subtracted if east. MH, an intermediate step in the conversion, obtained by applying variation to TH. Deviation, obtained from the deviation card on the aircraft, added to or subtracted from MH, as indicated. Compass heading, reading on the compass, found by applying deviation to MH, that is followed to remain on the desired course. Total distance, obtained by measuring the length of the TC line on the chart, using the scale at the bottom of the chart. GS, obtained by measuring the length of the TC line on the wind triangle, using the scale employed for drawing the diagram. Estimated time en route, ETE, total distance divided by GS. Fuel rate, predetermined gallons per hour used at cruising speed. Note, additional fuel for adequate reserve should be added as a safety measure. Flight planning. Title 14 of the Code of Federal Regulations, 14 CFR, Part 91 states, in part, that before beginning a flight, the pilot in command, PIC, of an aircraft shall become familiar with all available information concerning that flight. For flights not in the vicinity of an airport, this must include information on available current weather reports and forecasts, fuel requirements, alternatives available if the planned flight cannot be completed, and any known traffic delays of which the PIC has been advised by ATC. Assembling necessary material. The pilot should collect the necessary material well before beginning the flight. An appropriate current sectional chart and charts for areas adjoining the flight route should be among this material if the route of flight is near the border of a chart. Additional equipment should include a flight computer or electronic calculator, plotter, and any other item appropriate to the particular flight. For example, if a night flight is to be undertaken, carry a flashlight. If a flight is over desert country, carry a supply of water and other necessities. Weather check. It is wise to check the weather before continuing with other aspects of flight planning to see, first of all, if the flight is feasible and, if it is, which route is best. Chapter 12, Aviation Weather Services, discusses obtaining a weather briefing. Use of Chart Supplement US, formerly Airport, Facility Directory. Study available information about each airport at which a landing is intended. This should include a study of the notices to airmen, NOTAMs, and the Chart Supplement US, formerly Airport, Facility Directory. Figure 16 to 24. This includes location, elevation, runway and lighting facilities, available services, availability of Aeronautical Advisory Station frequency, UNICOM, types of fuel available, used to decide on refueling stops, FSS located on the airport, control tower and ground control frequencies, traffic information, remarks, and other pertinent information. The NOTAMs, issued every 28 days, should be checked for additional information on hazardous conditions or changes that have been made since issuance of the Chart Supplement US. The sectional chart bulletin subsection should be checked for major changes that have occurred since the last publication date of each sectional chart being used. Remember, the chart may be up to 6 months old. The effective date of the chart appears at the top of the front of the chart. The Chart Supplement US generally has the latest information pertaining to such matters and should be used in preference to the information on the back of the chart, if there are differences. Airplane Flight Manual or Pilot's Operating Handbook, AFM, PO. The Aircraft Flight Manual or Pilot's Operating Handbook, AFM, PO, should be checked to determine the proper loading of the aircraft, weight and balance data. The weight of the usable fuel and drainable oil aboard must be known. Also, check the weight of the passengers, the weight of all baggage to be carried, and the empty weight of the aircraft to be sure that the total weight does not exceed the maximum allowable weight. The distribution of the load must be known to tell if the resulting center of gravity, CG, is within limits. Be sure to use the latest weight and balance information in the FAA-approved AFM or other permanent aircraft records, as appropriate, to obtain empty weight and empty weight CG information. Determine the takeoff and landing distances from the appropriate charts, based on the calculated load, elevation of the airport, and temperature, then compare these distances with the amount of runway available. Remember, the heavier the load and the higher the elevation, temperature, or humidity, the longer the takeoff roll and landing roll and the lower the rate of climb. Check the fuel consumption charts to determine the rate of fuel consumption at the estimated flight altitude and power settings. Calculate the rate of fuel consumption and compare it with the estimated time for the flight so that refueling points along the route can be included in the plan. Charting the course. Once the weather has been checked and some preliminary planning completed, it is time to chart the course and determine the data needed to accomplish the flight. The following sections provide a logical sequence to follow in charting the course, complete a flight log, and filing a flight plan. In the following example, a trip is planned based on the following data and the sectional chart excerpt in Figure 16 to 25. Route of flight: Chickasha Airport direct to Guthrie Airport. True airspeed, TAS, equals 115 knots. Winds aloft equals 360 degrees at 10 knots. Usable fuel equals 38 gallons. Fuel rate equals 8 GPH. Deviation equals +2 degrees. Steps in charting the course. The following is a suggested sequence for arriving at the pertinent information for the trip. As information is determined, it may be noted as illustrated in the example of a flight log in Figure 16 to 26. Where calculations are required, the pilot may use a mathematical formula or a manual or electronic flight computer. If unfamiliar with the use of a manual or electronic computer, it would be advantageous to read the operation manual and work several practice problems at this point. First, draw a line from Chickasha Airport, point A, directly to Guthrie Airport, point F. The course line should begin at the center of the airport of departure and end at the center of the destination airport. If the route is direct, the course line consists of a single straight line. If the route is not direct, it consists of two or more straight line segments. For example, a VOR station that is off the direct route, but makes navigating easier, may be chosen. Radio navigation is discussed later in this chapter. Appropriate checkpoints should be selected along the route and noted in some way. These should be easy to locate points, such as large towns, large lakes and rivers, or combinations of recognizable points, such as towns with an airport, towns with a network of highways, and railroads entering and departing. Normally, choose only towns indicated by splashes of yellow on the chart. Do not choose towns represented by a small circle. These may turn out to be only a half dozen houses. In isolated areas, however, towns represented by a small circle can be prominent checkpoints. For this trip, 4 checkpoints have been selected. Checkpoint 1 consists of a tower located east of the course and can be further identified by the highway and railroad track, which almost parallels the course at this point. Checkpoint 2 is the obstruction just to the west of the course and can be further identified by Will Rogers World Airport, which is directly to the east. Checkpoint 3 is Wiley Post Airport, which the aircraft should fly directly over. Checkpoint 4 is a private, non-surfaced airport to the west of the course and can be further identified by the railroad track and highway to the east of the course. The course and areas on either side of the planned route should be checked to determine if there is any type of airspace with which the pilot should be concerned or which has special operational requirements. For this trip, it should be noted that the course passes through a segment of the Class C airspace surrounding Will Rogers World Airport, where the floor of the airspace is 2,500 feet mean sea level, MSL, and the ceiling is 5,300 feet MSL, point B. Also, there is Class D airspace from the surface to 3,800 feet MSL surrounding Wiley Post Airport, point C, during the time the control tower is in operation. Study the terrain and obstructions along the route. This is necessary to determine the highest and lowest elevations, as well as the highest obstruction to be encountered, so an appropriate altitude that conforms to 14 CFR Part 91 regulations can be selected. If the flight is to be flown at an altitude of more than 3,000 feet above the terrain, conformance to the cruising altitude appropriate to the direction of flight is required. Check the route for particularly rugged terrain so it can be avoided. Areas where a takeoff or landing is made should be carefully checked for tall obstructions. Television transmitting towers may extend to altitudes over 1,500 feet above the surrounding terrain. It is essential that pilots be aware of their presence and location. For this trip, it should be noted that the tallest obstruction is part of a series of antennas with a height of 2,749 feet MSL, point D. The highest elevation should be located in the northeast quadrant and is 2,900 feet MSL, point E. Since the wind is no factor and it is desirable and within the aircraft's capability to fly above the Class C and D airspace to be encountered, an altitude of 5,500 feet MSL is chosen. This altitude also gives adequate clearance of all obstructions, as well as conforms to the 14 CFR Part 91 requirement to fly at an altitude of odd 1,000 plus 500 feet when on a magnetic course between 0 and 179 degrees. Next, the pilot should measure the total distance of the course, as well as the distance between checkpoints. The total distance is 53 nanometer, and the distance between checkpoints is as noted on the flight log in Figure 16 to 26. After determining the distance, the TC should be measured. If using a plotter, follow the directions on the plotter. The TC is 031 degree. Once the TH is established, the pilot can determine the compass heading. This is done by following the formula given earlier in this chapter. The formula is TC plus or minus WCA equals TH plus or minus V equals MH plus or minus D equals CH. The WCA can be determined by using a manual or electronic flight computer. Using a wind of 360 degrees at 10 knots, it is determined the WCA is 3 degrees left. This is subtracted from the TC, making the TH 28 degrees. Next, the pilot should locate the isogonic line closest to the route of the flight to determine variation. Figure 16 to 25 shows the variation to be 6.30 degrees east, rounded to 7 degrees east, which means it should be subtracted from the TH, giving an MH of 21 degrees. Next, add 2 degrees to the MH for the deviation correction. This gives the pilot the compass heading of 23 degrees. Now, the GS can be determined. This is done using a manual or electronic calculator. The GS is determined to be 106 knots. Based on this information, the total trip time, as well as time between checkpoints, and the fuel burned can be determined. These numbers can be calculated by using a manual or electronic calculator. For this trip, the GS is 106 knots and the total time is 35 minutes, 30 minutes plus 5 minutes for climb, with a fuel burn of 4.7 gallons. Refer to the flight log in Figure 16 to 26 for the time between checkpoints. As the trip progresses, the pilot can note headings and time and make adjustments in heading, GS, and time. Filing a VFR flight plan. Filing a flight plan is not required by regulations. However, it is a good operating practice since the information contained in the flight plan can be used in search and rescue in the event of an emergency. Flight plans can be filed in the air by radio, but it is best to file a flight plan by phone just before departing. After takeoff, contact the FSS by radio and give them the takeoff time so the flight plan can be activated. When a VFR flight plan is filed, it is held by the FSS until 1 hour after the proposed departure time and then cancelled unless the actual departure time is received, a revised proposed departure time is received, or at the time of filing, the FSS is informed that the proposed departure time is met, but actual time cannot be given because of inadequate communication. The FSS specialist who accepts the flight plan does not inform the pilot of this procedure, however. Figure 16 to 27 shows the flight plan form a pilot files with the FSS. When filing a flight plan by telephone or radio, give the information in the order of the numbered spaces. This enables the FSS specialist to copy the information more efficiently. Most of the fields are either self-explanatory or non-applicable to the VFR flight plan, such as item 13. However, some fields may need explanation. Item 3 is the aircraft type and special equipment. An example would be C-150X, which means the aircraft has no transponder. A listing of special equipment codes is found in the Aeronautical Information Manual, AIM. Item 6 is the proposed departure time in UTC, indicated by the Z. Item 7 is the cruising altitude. Normally, VFR can be entered in this block since the pilot chooses a cruising altitude to conform to FAA regulations. Item 8 is the route of flight. If the flight is to be direct, enter the word direct. If not, enter the actual route to be followed, such as via certain towns or navigation aids. Item 10 is the estimated time en route. In the sample flight plan, 5 minutes was added to the total time to allow for the climb. Item 12 is the fuel on board in hours and minutes. This is determined by dividing the total usable fuel aboard in gallons by the estimated rate of fuel consumption in gallons. Remember, there is every advantage in filing a flight plan, but do not forget to close the flight plan upon arrival. This should be done via telephone to avoid radio congestion. Ground-based navigation. Advances in navigational radio receivers installed in aircraft, the development of aeronautical charts that show the exact location of ground transmitting stations and their frequencies, along with refined flight deck instrumentation make it possible for pilots to navigate with precision to almost any point desired. Although precision in navigation is obtainable through the proper use of this equipment, beginning pilots should use this equipment to supplement navigation by visual reference to the ground, pilotage. This method provides the pilot with an effective safeguard against disorientation in the event of radio malfunction. There are 3 radio navigation systems available for use for VFR navigation. These are VHF Omnidirectional Range, VOR, Non-Directional Radio Beacon, NDB, Global Positioning System, GPS, Very High Frequency, VHF, Omnidirectional Range, VOR. The VOR system is present in 3 slightly different navigation aids: NAVAIDs, VOR, Distance Measuring Equipment, DME, discussed in a later section, and VOR-TAC. By itself it is known as a VOR, and it provides magnetic bearing information to and from the station. When DME is also installed with a VOR, the NAVAID is referred to as a VOR, DME. When military tactical air navigation, TACAN, equipment is installed with a VOR, the NAVAID is known as a VOR-TAC. DME is always an integral part of a VOR-TAC. Regardless of the type of NAVAID utilized, VOR, VOR, DME, or VOR-TAC, the VOR indicator behaves the same. Unless otherwise noted in this section, VOR, VOR, DME, and VOR-TAC and aviators are all referred to hereafter as VORs. The prefix, omni, means all, and an omnidirectional range is a VHF radio transmitting ground station that projects straight-line courses, radials, from the station in all directions. From a top view, it can be visualized as being similar to the spokes from the hub of a wheel. The distance VOR radials are projected depends upon the power output of the transmitter. The course or radials projected from the station are referenced to MN. Therefore, a radial is defined as a line of magnetic bearing extending outward from the VOR station. Radials are identified by numbers beginning with 001, which is 1 degree east of MN, and progress in sequence through all the degrees of a circle until reaching 360. To aid in orientation, a compass rose reference to magnetic north is superimposed on aeronautical charts at the station location. VOR ground stations transmit within a VHF frequency band of 108.0 to 117.95 MHz. Because the equipment is VHF, the signals transmitted are subject to line-of-sight restrictions. Therefore, its range varies in direct proportion to the altitude of receiving equipment. Generally, the reception range of the signals at an altitude of 1,000 feet above ground level, AGL, is about 40 to 45 miles. This distance increases with altitude. VORs and VOR-TACs are classed according to operational use. There are 3 classes: T, terminal; L, low altitude; H, high altitude. The useful range of certain facilities may be less than 50 miles. For further information concerning these restrictions, refer to the Communication, NAVAID remarks in the Chart Supplement US. The accuracy of course alignment of VOR radials is considered to be excellent. It is generally within plus or minus 1 degree. However, certain parts of the VOR receiver equipment deteriorate, affecting its accuracy. This is particularly true at great distances from the VOR station. The best assurance of maintaining an accurate VOR receiver is periodic checks and calibrations. VOR accuracy checks are not a regulatory requirement for VFR flight. However, to assure accuracy of the equipment, these checks should be accomplished quite frequently and a complete calibration should be performed each year. The following means are provided for pilots to check VOR accuracy. FAA VOR Test Facility, VOT. Certified Airborne Checkpoints. Certified ground checkpoints located on airport surfaces. If an aircraft has 2 VOR receivers installed, a dual VOR receiver check can be made. To accomplish the dual receiver check, a pilot must tune both VOR receivers to the same VOR ground facility. The maximum permissible variation between the 2 indicated bearings is 4 degrees. A list of the airborne and ground checkpoints is published in the Chart Supplement US. Basically, these checks consist of verifying that the VOR radials the aircraft equipment receives are aligned with the radials the station transmits. There are not specific tolerances in VOR checks required for VFR flight. But as a guide to assure acceptable accuracy, the required IFR tolerances can be used, plus or minus 4 degrees for ground checks and plus or minus 6 degrees for airborne checks. These checks can be performed by the pilot. The VOR transmitting station can be positively identified by its Morse code identification or by a recorded voice identification that states the name of the station followed by VOR. Many FSSs transmit voice messages on the same frequency that the VOR operates. Voice transmissions should not be relied upon to identify stations because many FSSs remotely transmit over several omniranges that have names different from that of the transmitting FSS. If the VOR is out of service for maintenance, the coded identification is removed and not transmitted. This serves to alert pilots that this station should not be used for navigation. VOR receivers are designed with an alarm flag to indicate when signal strength is inadequate to operate the navigational equipment. This happens if the aircraft is too far from the VOR or the aircraft is too low and, therefore, is out of the line of sight of the transmitting signals. Using the VOR. In review, for VOR radio navigation, there are two components required: ground transmitter and aircraft receiving equipment. The ground transmitter is located at a specific position on the ground and transmits on an assigned frequency. The aircraft equipment includes a receiver with a tuning device and a VOR or Omni navigation instrument. The navigation instrument could be a course deviation indicator, CDI, horizontal situation indicator, HSI, or a radiomagnetic indicator, RMI. Each of these instruments indicates the course to the tuned VOR. Course deviation indicator, CDI. The CDI is found in most training aircraft. It consists of an omnibearing selector, OBS, sometimes referred to as the course selector, a CDI needle, left-right needle, and a 2 from indicator. The course selector is an azimuth dial that can be rotated to select a desired radial or to determine the radial over which the aircraft is flying. In addition, the magnetic course, TO, or from the station can be determined. When the course selector is rotated, it moves the CDI or needle to indicate the position of the radial relative to the aircraft. If the course selector is rotated until the deviation needle is centered, the radial, magnetic course, from the station, or its reciprocal, magnetic course, TO, the station, can be determined. The course deviation needle also moves to the right or left if the aircraft is flown or drifting away from the radial which is set in the course selector. By centering the needle, the course selector indicates either the course, from the station, or the course, TO, the station. If the flag displays a TO, the course shown on the course selector must be flown to the station. Figure 16 to 29, if from is displayed and the course shown is followed, the aircraft is flown away from the station. Horizontal situation indicator. The HSI is a direction indicator that uses the output from a flux valve to drive the compass card. The HSI, figure 16 to 30, combines the magnetic compass with navigation signals and a glider slope. The HSI gives the pilot an indication of the location of the aircraft in relation to the chosen course or radial. In figure 16 to 30, the aircraft magnetic heading displayed on the compass card under the lubber line is 184 degrees. The course select pointer shown is set to 295 degrees. The tail of the pointer indicates the reciprocal, 115 degrees. The course deviation bar operates with a VOR, localizer, VOR, lock, or GPS navigation receiver to indicate left or right deviations from the course selected with the course select pointer. Operating in the same manner, the angular movement of a conventional VOR, lock needle indicates deviation from course. The desired course is selected by rotating the course select pointer, in relation to the compass card, by means of the course select knob. The HSI has a fixed aircraft symbol and the course deviation bar displays the aircraft's position relative to the selected course. The 2 from indicator is a triangular pointer. When the indicator points to the head of the course select pointer, the arrow shows the course selected. If properly intercepted and flown, the course takes the aircraft to the chosen facility. When the indicator points to the tail of the course, the arrow shows that the course selected, if properly intercepted and flown, takes the aircraft directly away from the chosen facility. When the nav warning flag appears, it indicates no reliable signal is being received. The appearance of the HDG flag indicates the compass card is not functioning properly. Radiomagnetic indicator, RMI. The RMI is a navigational aid providing aircraft magnetic or directional gyro heading and very high-frequency omnidirectional range, VOR, GPS, and automatic direction finder, ADF, bearing information. Figures 16 to 31. Remote indicating compasses were developed to compensate for errors in and limitations of older types of heading indicators. The remote compass transmitter is a separate unit usually mounted in a wingtip to eliminate the possibility of magnetic interference. The RMI consists of a compass card, a heading index, two bearing pointers, and pointer function switches. The two pointers are driven by any two combinations of a GPS, an ADF, and/or a VOR. The pilot has the ability to select the navigation aid to be indicated. The pointer indicates the course to the selected NAVAID or waypoint. In Figure 16 to 31, the green pointer is indicating the station tuned on the ADF. The yellow pointer is indicating the course to a VOR or GPS waypoint. Note that there is no requirement for a pilot to select a course with the RMI. Only the selected navigation source is pointed to by the needles. Tracking with VOR. The following describes a step-by-step procedure for tracking to and from a VOR station using a CDI. Figure 16 to 32 illustrates the procedure. First, tune the VOR receiver to the frequency of the selected VOR station. For example, 115.0 to receive Bravo VOR. Next, check the identifiers to verify that the desired VOR is being received. As soon as the VOR is properly tuned, the course deviation needle deflects either left or right. Then, rotate the azimuth dial to the course selector until the course deviation needle centers and the TO from indicator indicates to. If the needle centers with a from indication, the azimuth should be rotated 180 degrees because, in this case, it is desired to fly TO, the station. Now, turn the aircraft to the heading indicated on the VOR azimuth dial or course selector, 350 degrees in this example. If a heading of 350 degrees is maintained with a wind from the right as shown, the aircraft drifts to the left of the intended track. As the aircraft drifts off course, the VOR course deviation needle gradually moves to the right of center or indicates the direction of the desired radial or track. To return to the desired radial, the aircraft heading must be altered to the right. As the aircraft returns to the desired track, the deviation needle slowly returns to center. When centered, the aircraft is on the desired radial and a left turn must be made toward, but not to the original heading of 350 degrees because a wind drift correction must be established. The amount of correction depends upon the strength of the wind. If the wind velocity is unknown, a trial and error method can be used to find the correct heading. Assume, for this example, a 10 degrees correction for a heading of 360 degrees is maintained. While maintaining a heading of 360 degrees, assume that the course deviation begins to move to the left. This means that the wind correction of 10 degrees is too great and the aircraft is flying to the right of course. A slight turn to the left should be made to permit the aircraft to return to the desired radial. When the deviation needle centers, a small wind drift correction of 5 degrees or a heading correction of 355 degrees should be flown. If this correction is adequate, the aircraft remains on the radial. If not, small variations in heading should be made to keep the needle centered and consequently keep the aircraft on the radial. As the VOR station is passed, the course deviation needle fluctuates, then settles down, and the TO indication changes to from. If the aircraft passes to one side of the station, the needle deflects in the direction of the station as the indicator changes to from. Generally, the same techniques apply when tracking outbound as those used for tracking inbound. If the intent is to fly over the station and track outbound on the reciprocal of the inbound radial, the course selector should not be changed. Corrections are made in the same manner to keep the needle centered. The only difference is that the omnidirectional range indicator indicates from. If tracking outbound on a course other than the reciprocal of the inbound radial, this new course or radial must be set in the course selector and a turn made to intercept this course. After this course is reached, tracking procedures are the same as previously discussed. Tips on using the VOR. Positively identify the station by its code or voice identification. Remember that VOR signals are line of sight. A weak signal or no signal at all is received if the aircraft is too low or too far from the station. When navigating to a station, determine the inbound radial and use this radial. Fly a heading that will maintain the course. If the aircraft drifts, fly a heading to re-intercept the course, then apply a correction to compensate for wind drift. If minor needle fluctuations occur, avoid changing headings immediately. Wait a moment to see if the needle recenters. If it does not, then you must correctly recenter the course to the needle. When flying TO, a station, always fly the selected course with a TO indication. When flying from a station, always fly the selected course with a from indication. If this is not done, the action of the course deviation needle is reversed. To further explain this reverse action, if the aircraft is flown toward a station with a from indication or away from a station with a TO indication, the course deviation needle indicates in a direction opposite to that which it should indicate. For example, if the aircraft drifts to the right of a radial being flown, the needle moves to the right or points away from the radial. If the aircraft drifts to the left of the radial being flown, the needle moves left or in the direction opposite of the radial. When navigating using the VOR, it is important to fly headings that maintain or re-intercept the course. Just turning toward the needle will cause overshooting the radial and flying an S-turn to the left and right of course. Time and distance check from a station using a RMI. To compute time and distance from a station, first turn the aircraft to place the RMI bearing pointer on the nearest 90 degrees index. Note the time and maintain the heading. When the RMI bearing pointer has moved 10 degrees, note the elapsed time in seconds and apply the formulas in the following example to determine the approximate time and distance from a given station. The time from station may also be calculated by using a short method based on the above formula, if a 10 degrees bearing change is flown. If the elapsed time for the bearing change is noted in seconds and a 10 degrees bearing change is made, the time from the station, in minutes, is determined by counting off 1 decimal point. Thus, if 75 seconds are required to fly a 10 degrees bearing change, the aircraft is 7.5 minutes from the station. When the RMI bearing pointer is moving rapidly or when several corrections are required to place the pointer on the wingtip position, the aircraft is at station passage. The distance from the station is computed by multiplying TAS or GS, in miles per minute, by the previously determined time in minutes. For example, if the aircraft is 7.5 minutes from station, flying at a TAS of 120 knots or 2 nanometer per minute, the distance from station is 15 nanometer, 7.5 times 2 equals 15. The accuracy of time and distance checks is governed by existing wind, degree of bearing change, and accuracy of timing. The number of variables involved causes the result to be only an approximation. However, by flying an accurate heading and checking the time and bearing closely, the pilot can make a reasonable estimate of time and distance from the station. Time and distance check from a station using a CDI. To compute time and distance from a station using a CDI, first tune and identify the VOR station and determine the radial on which you are located. Then turn inbound and re-center the needle if necessary. Turn 90 degrees left or right of the inbound course, rotating the OBS to the nearest 10 degrees increment opposite the direction of turn. Maintain heading and when the CDI centers, note the time. Maintaining the same heading, rotate the OBS 10 degrees in the same direction as was done previously and note the elapsed time when the CDI again centers. Time and distance from the station is determined from the formula shown in figure 16 to 34. Course intercept. Course interceptions are performed in most phases of instrument navigation. The equipment used varies, but an intercept heading must be flown that results in an angle or rate of intercept sufficient for solving a particular problem. Rate of intercept. Rate of intercept, seen by the aviator as bearing pointer or HSI movement, is a result of the following factors. The angle at which the aircraft is flown toward a desired course, angle of intercept. True airspeed and wind, GS. Distance from the station. Angle of intercept. The angle of intercept is the angle between the heading of the aircraft, intercept heading, and the desired course. Controlling this angle by selection, adjustment of the intercept heading is the easiest and most effective way to control course interceptions. Angle of intercept must be greater than the degrees from course, but should not exceed 90 degrees. Within this limit, make adjustments as needed to achieve the most desirable rate of intercept. When selecting an intercept heading, the key factor is the relationship between distance from the station and degrees from the course. Each degree, or radial, is 1 nanometer wide at a distance of 60 nanometer from the station. Width increases or decreases in proportion to the 60 nanometer distance. For example, 1 degree is 2 nanometer wide at 120 nanometer, and 1/2 nm wide at 30 nanometer. For a given GS and angle of intercept, the resultant rate of intercept varies according to the distance from the station. When selecting an intercept heading to form an angle of intercept, consider the following factors. Degrees from course. Distance from the station. True airspeed and wind, GS. Distance measuring equipment, DME. Distance measuring equipment, DME, consists of an ultra-high frequency, UHF, navigational aid with VOR, DMEs and VORTACs. It measures, in nanometer, the slant range distance of an aircraft from a VOR, DME or VORTAC, both hereafter referred to as a VORTAC. Although DME equipment is very popular, not all aircraft are DME equipped. To utilize DME, the pilot should select, tune, and identify a VORTAC, as previously described. The DME receiver, utilizing what is called a paired frequency concept, automatically selects and tunes the UHF DME frequency associated with the VHF VORTAC frequency selected by the pilot. This process is entirely transparent to the pilot. After a brief pause, the DME display shows the slant range distance to or from the VORTAC. Slant range distance is the direct distance between the aircraft and the VORTAC and is therefore affected by aircraft altitude. Station passage directly over a VORTAC from an altitude of 6,076 feet AGL would show approximately 1.0 nanometer on the DME. DME is a very useful adjunct to VOR navigation. A VOR radial alone merely gives line of position information. With DME, a pilot may precisely locate the aircraft on a given line, radial. Most DME receivers also provide GS and time to station modes of operation. The GS is displayed in knots, nmph. The time to station mode displays the minutes remaining to VORTAC station passage, predicated upon the present GS. GS and time to station information is only accurate when tracking directly to or from a VORTAC. DME receivers typically need a minute or two of stabilized flight directly to or from a VORTAC before displaying accurate GS or time to station information. Some DME installations have a hold feature that permits a DME signal to be retained from one VORTAC while the course indicator displays course deviation information from an ILS or another VORTAC. VOR, DME RNAV. Area navigation, RNAV, permits electronic course guidance on any direct route between points established by the pilot. While RNAV is a generic term that applies to a variety of NAVAIDs, such as GPS and others, this section deals with VOR, DME-based RNAV. VOR, DME-RNAV is not a separate ground-based NAVAID, but a method of navigation using VOR, DME and VORTAC signals specially processed by the aircraft's RNAV computer. Note: in this section, the term VORTAC also includes VOR, DME NAVAIDs. In its simplest form, VOR, DME RNAV allows the pilot to electronically move VORTACs around to more convenient locations. Once electronically relocated, they are referred to as waypoints. These waypoints are described as a combination of a selected radial and distance within the service volume of the VORTAC to be used. These waypoints allow a straight course to be flown between almost any origin and destination, without regard to the orientation of VORTACs or the existence of airways. While the capabilities and methods of operation of VOR, DME RNAV units differ, there are basic principles of operation that are common to all. Pilots are urged to study the manufacturer's operating guide and receive instruction prior to the use of VOR, DME RNAV or any unfamiliar navigational system. Operational information and limitations should also be sought from placards and the supplement section of the AFM, PO. VOR, DME-based RNAV units operate in at least 3 modes: VOR, en route, and approach. A 4th mode, VOR parallel, may also be found on some models. The units need both VOR and DME signals to operate in any RNAV mode. If the NAVAID selected is a VOR without DME, RNAV mode will not function. In the VOR, or non-RNAV, mode, the unit simply functions as a VOR receiver with DME capability. Figure 16-36. The unit's display on the VOR indicator is conventional in all respects. For operation on established airways or any other ordinary VOR navigation, the VOR mode is used. To utilize the unit's RNAV capability, the pilot selects and establishes a waypoint or a series of waypoints to define a course. A VORTAC, or VOR, DME, needs to be selected as a NAVAID, since both radial and distance signals are available from these stations. To establish a waypoint, a point somewhere within the service range of a VORTAC is defined on the basis of radial and distance. Once the waypoint is entered into the unit and the RNAV en route mode is selected, the CDI displays course guidance to the waypoint, not the original VORTAC. DME also displays distance to the waypoint. Many units have the capability to store several waypoints, allowing them to be programmed prior to flight, if desired, and called up in flight. RNAV waypoints are entered into the unit in magnetic bearings, radials, of degrees and tenths, i.e., 275.5 degrees, and distances in nanometer and tenths, i.e., 25.2 nanometer. When plotting RNAV waypoints on an aeronautical chart, pilots find it difficult to measure to that level of accuracy, and in practical application, it is rarely necessary. A number of flight planning publications publish airport coordinates and waypoints with this precision, and the unit accepts those figures. There is a subtle but important difference in CDI operation and display in the RNAV modes. In the RNAV modes, course deviation is displayed in terms of linear deviation. In the RNAV en route mode, maximum deflection of the CDI typically represents 5 nanometer on either side of the selected course without regard to distance from the waypoint. In the RNAV approach mode, maximum deflection of the CDI typically represents 1¼ nm on either side of the selected course. There is no increase in CDI sensitivity as the aircraft approaches a waypoint in RNAV mode. The RNAV approach mode is used for instrument approaches. Its narrow scale width, 1/4 of the en route mode, permits very precise tracking to or from the selected waypoint. In VFR cross-country navigation, tracking a course in the approach mode is not desirable because it requires a great deal of attention and soon becomes tedious. A fourth, lesser used mode on some units is the VOR parallel mode. This permits the CDI to display linear, not angular, deviation as the aircraft tracks to and from VOR/TACs. It derives its name from permitting the pilot to offset, or parallel, a selected course or airway at a fixed distance of the pilot's choosing, if desired. The VOR parallel mode has the same effect as placing a waypoint directly over an existing VOR/TAC. Some pilots select the VOR parallel mode when utilizing the navigation, NAV, tracking function of their autopilot for smoother course following near the VOR/TAC. Navigating an aircraft with VOR, DME-based RNAV can be confusing, and it is essential that the pilot become familiar with the equipment installed. It is not unknown for pilots to operate inadvertently in one of the RNAV modes when the operation was not intended, by overlooking switch positions or annunciators. The reverse has also occurred with a pilot neglecting to place the unit into one of the RNAV modes by overlooking switch positions or annunciators. As always, the prudent pilot is not only familiar with the equipment used, but never places complete reliance in just one method of navigation when others are available for cross-check. Automatic Direction Finder, ADF. Many general aviation type aircraft are equipped with ADF radio receiving equipment. To navigate using the ADF, the pilot tunes the receiving equipment to a ground station known as a non-directional radio beacon, NDB. The NDB stations normally operate in a low or medium frequency band of 200 to 415 kHz. The frequencies are readily available on Aeronautical charts or in the chart supplement US. All radio beacons, except compass locators, transmit a continuous 3-letter identification in code, except during voice transmissions. A compass locator, which is associated with an instrument landing system, transmits a 2-letter identification. Standard broadcast stations can also be used in conjunction with ADF. Positive identification of all radio stations is extremely important, and this is particularly true when using standard broadcast stations for navigation. NDBs have one advantage over the VOR in that low or medium frequencies are not affected by line of sight. The signals follow the curvature of the Earth. Therefore, if the aircraft is within the range of the station, the signals can be received regardless of altitude. One of the disadvantages that should be considered when using low frequency, LF, for navigation is that LF signals are very susceptible to electrical disturbances, such as lightning. These disturbances create excessive static, needle deviations, and signal fades. There may be interference from distant stations. Pilots should know the conditions under which these disturbances can occur so they can be more alert to possible interference when using the ADF. Basically, the ADF aircraft equipment consists of a tuner, which is used to set the desired station frequency, and the navigational display. The navigational display consists of a dial upon which the azimuth is printed and a needle which rotates around the dial and points to the station to which the receiver is tuned. Some of the ADF dials can be rotated to align the azimuth with the aircraft heading. Others are fixed with 0 degrees representing the nose of the aircraft and 180 degrees representing the tail. Only the fixed azimuth dial is discussed in this handbook. Figure 16 to 38 illustrates terms that are used with the ADF and should be understood by the pilot. To determine the magnetic bearing, from the station, 180 degrees is added to or subtracted from the magnetic bearing to the station. This is the reciprocal bearing and is used when plotting position fixes. Keep in mind that the needle of fixed azimuth points to the station in relation to the nose of the aircraft. If the needle is deflected 30 degrees to the left for a relative bearing of 330 degrees, this means that the station is located 30 degrees left. If the aircraft is turned left 30 degrees, the needle moves to the right 30 degrees and indicates a relative bearing of 0 degrees, meaning that the aircraft is pointing toward the station. If the pilot continues flight toward the station keeping the needle on 0 degrees, the procedure is called homing to the station. If a crosswind exists, the ADF needle continues to drift away from 0. To keep the needle on 0, the aircraft must be turned slightly, resulting in a curved flight path to the station. Homing to the station is a common procedure but may result in drifting downwind, thus lengthening the distance to the station. Tracking to the station requires correcting for wind drift and results in maintaining flight along a straight track or bearing to the station. When the wind drift correction is established, the ADF needle indicates the amount of correction to the right or left. For instance, if the magnetic bearing to the station is 340 degrees, a correction for a left crosswind would result in a magnetic heading of 330 degrees, and the ADF needle would indicate 10 degrees to the right or a relative bearing of 010 degree. When tracking away from the station, wind corrections are made similar to tracking to the station, but the ADF needle points toward the tail of the aircraft or the 180 degrees position on the azimuth dial. Attempting to keep the ADF needle on the 180 degrees position during winds results in the aircraft flying a curved flight leading further and further from the desired track. When tracking outbound, corrections for wind should be made in the direction opposite of that in which the needle is pointing. Although the ADF is not as popular as the VOR for radio navigation, with proper precautions and intelligent use, the ADF can be a valuable aid to navigation. Global Positioning System. The GPS is a satellite-based radio navigation system. Its RNAV guidance is worldwide in scope. There are no symbols for GPS on aeronautical charts as it is a space-based system with global coverage. Development of the system is underway so that GPS is capable of providing the primary means of electronic navigation. Portable and yoke-mounted units are proving to be very popular in addition to those permanently installed in the aircraft. Extensive navigation databases are common features in aircraft GPS receivers. The GPS is a satellite radio navigation and time dissemination system developed and operated by the U.S. Department of Defense, DoD. Civilian interface and GPS system status is available from the U.S. Coast Guard. It is not necessary to understand the technical aspects of GPS operation to use it in VFR, IFR navigation. It does differ significantly from conventional, ground-based electronic navigation, and awareness of those differences is important. Awareness of equipment approvals and limitations is critical to the safety of flight. The GPS navigation system broadcasts a signal that is used by receivers to determine precise position anywhere in the world. The receiver tracks multiple satellites and determines a pseudo-orange measurement to determine the user location. A minimum of 4 satellites is necessary to establish an accurate 3-dimensional position. The Department of Defense, DoD, is responsible for operating the GPS satellite constellation and monitors the GPS satellites to ensure proper operation. The status of a GPS satellite is broadcast as part of the data message transmitted by the satellite. GPS status information is also available from the U.S. Coast Guard Navigation Information Service at 703-313-5907 or online at www.navchen.uscg.gov. Additionally, satellite status is available through the NOTAM system. The GPS receiver verifies the integrity, usability, of the signals received from the GPS constellation through Receiver Autonomous Integrity Monitoring, RAIM, to determine if a satellite is providing corrupted information. At least one satellite, in addition to those required for navigation, must be in view for the receiver to perform the RAIM function. Thus, RAIM needs a minimum of 5 satellites in view or 4 satellites and a barometric altimeter, baro aiding, to detect an integrity anomaly. For receivers capable of doing so, RAIM needs 6 satellites in view, or 5 satellites with baro aiding, to isolate the corrupt satellite signal and remove it from the navigation solution. Baro aiding is a method of augmenting the GPS integrity solution by using a non-satellite input source. GPS-derived altitude should not be relied upon to determine aircraft altitude, since the vertical error can be quite large and no integrity is provided. To ensure that baro aiding is available, the current altimeter setting must be entered into the receiver as described in the operating manual. RAIM messages vary somewhat between receivers. However, generally there are 2 types. One type indicates that there are not enough satellites available to provide RAIM integrity monitoring, and another type indicates that the RAIM integrity monitor has detected a potential error that exceeds the limit for the current phase of flight. Without RAIM capability, the pilot has no assurance of the accuracy of the GPS position. Selective availability. Selective availability, SA, is a method by which the accuracy of GPS is intentionally degraded. This feature is designed to deny hostile use of precise GPS positioning data. SA was discontinued on May 1, 2000, but many GPS receivers are designed to assume that SA is still active. The baseline GPS satellite constellation consists of 24 satellites positioned in 6 Earth-centered orbital planes with 4 operation satellites and a spare satellite slot in each orbital plane. The system can support a constellation of up to 30 satellites in orbit. The orbital period of a GPS satellite is 1/2 of a sidereal day, or 11 hours 58 minutes. The orbits are nearly circular and equally spaced about the equator at a 60-degree separation, with an inclination of 55 degrees relative to the equator. The orbital radius, i.e., distance from the center of mass of the Earth to the satellite, is approximately 26,600 kilometers. With the baseline satellite constellation, users with a clear view of the sky have a minimum of 4 satellites in view. It is more likely that a user would see 6 to 8 satellites. The satellites broadcast ranging signals and navigation data, allowing users to measure their pseudoranges in order to estimate their position, velocity and time, in a passive, listen-only mode. The receiver uses data from a minimum of 4 satellites above the mask angle, the lowest angle above the horizon at which a receiver can use a satellite. The exact number of satellites operating at any one particular time varies depending on the number of satellite outages and operational spares in orbit. For current status of the GPS constellation, please visit http://tycho.usno.navy.mil/jeepsker.html. VFR use of GPS. GPS navigation has become a great asset to VFR pilots, providing increased navigation capability and enhanced situational awareness while reducing operating costs due to greater ease in flying direct routes. While GPS has many benefits to the VFR pilot, care must be exercised to ensure that system capabilities are not exceeded. Types of receivers used for GPS navigation under VFR are varied, from a full IFR installation being used to support a VFR flight to a VFR-only installation, in either a VFR or IFR-capable aircraft, to a handheld receiver. The limitations of each type of receiver installation or use must be understood by the pilot to avoid misusing navigation information. In all cases, VFR pilots should never rely solely on one system of navigation. GPS navigation must be integrated with other forms of electronic navigation, as well as pilotage and dead reckoning. Only through the integration of these techniques can the VFR pilot ensure accuracy in navigation. Some critical concerns in VFR use of GPS include RAM capability, database currency, and antenna location. RAM capability. Many VFR GPS receivers and all handheld units are not equipped with RAM alerting capability. Loss of the required number of satellites in view, or the detection of a position error, cannot be displayed to the pilot by such receivers. In receivers with no RAM capability, no alert would be provided to the pilot that the navigation solution had deteriorated and an undetected navigation error could occur. A systematic cross-check with other navigation techniques would identify this failure and prevent a serious deviation. In many receivers, an updatable database is used for navigation fixes, airports, and instrument procedures. These databases must be maintained to the current update for IFR operation, but no such requirement exists for VFR use. However, in many cases, the database drives a moving map display that indicates special use airspace and the various classes of airspace in addition to other operational information. Without a current database, the moving map display may be outdated and offer erroneous information to VFR pilots wishing to fly around critical airspace areas, such as a restricted area or a Class B airspace segment. Numerous pilots have ventured into airspace they were trying to avoid by using an outdated database. If there is not a current database in the receiver, disregard the moving map display when making critical navigation decisions. In addition, waypoints are added, removed, relocated, or renamed as required to meet operational needs. When using GPS to navigate relative to a named fix, a current database must be used to properly locate a named waypoint. Without the update, it is the pilot's responsibility to verify the waypoint location referencing to an official current source, such as the chart supplement US, sectional chart, or en route chart. In many VFR installations of GPS receivers, antenna location is more a matter of convenience than performance. In IFR installations, care is exercised to ensure that an adequate clear view is provided for the antenna to communicate with satellites. If an alternate location is used, some portion of the aircraft may block the view of the antenna, increasing the possibility of losing navigation signal. This is especially true in the case of handheld receivers. The use of handheld receivers for VFR operations is a growing trend, especially among rental pilots. Typically, suction cups are used to place the GPS antennas on the inside of aircraft windows. While this method has great utility, the antenna location is limited by aircraft structure for optimal reception of available satellites. Consequently, signal loss may occur in certain situations where aircraft satellite geometry causes a loss of navigation signal. These losses, coupled with a lack of RAM capability, could present erroneous position and navigation information with no warning to the pilot. While the use of handheld GPS receivers for VFR operations is not limited by regulation, modification of the aircraft, such as installing a panel or yoke-mounted holder, is governed by 14 CFR Part 43. Pilots should consult a mechanic to ensure compliance with the regulation and a safe installation. Tips for using GPS for VFR operations. Always check to see if the unit has RAM capability. If no RAM capability exists, be suspicious of a GPS displayed position when any disagreement exists with the position derived from other radio navigation systems, pilotage, or dead reckoning. Check the currency of the database, if any. If expired, update the database using the current revision. If an update of an expired database is not possible, disregard any moving map display of airspace for critical navigation decisions. Be aware that named waypoints may no longer exist or may have been relocated since the database expired. At a minimum, the waypoints to be used should be verified against a current official source, such as the chart supplement US or a sectional aeronautical chart. While a handheld GPS receiver can provide excellent navigation capability to VFR pilots, be prepared for intermittent loss of navigation signal, possibly with no RAIM warning to the pilot. If mounting the receiver in the aircraft, be sure to comply with 14 CFR Part 43. Plan flights carefully before taking off. If navigating to user-defined waypoints, enter them prior to flight, not on the fly. Verify the planned flight against a current source, such as a current sectional chart. There have been cases in which one pilot used waypoints created by another pilot that were not where the pilot flying was expecting. This generally resulted in a navigation error. Minimize head-down time in the aircraft and maintain a sharp lookout for traffic, terrain, and obstacles. Just a few minutes of preparation and planning on the ground makes a great difference in the air. Another way to minimize head-down time is to become very familiar with the receiver's operation. Most receivers are not intuitive. The pilot must take the time to learn the various keystrokes, knob functions, and displays that are used in the operation of the receiver. Some manufacturers provide computer-based tutorials or simulations of their receivers. Take the time to learn about the particular unit before using it in flight. In summary, be careful not to rely on GPS to solve all VFR navigational problems. Unless an IFR receiver is installed in accordance with IFR requirements, no standard of accuracy or integrity can be assured. While the practicality of GPS is compelling, the fact remains that only the pilot can navigate the aircraft, and GPS is just one of the pilot's tools to do the job. VFR waypoints. VFR waypoints provide VFR pilots with a supplementary tool to assist with position awareness while navigating visually in aircraft equipped with area navigation receivers. VFR waypoints should be used as a tool to supplement current navigation procedures. The use of VFR waypoints include providing navigational aids for pilots unfamiliar with an area, waypoint definition of existing reporting points, enhanced navigation in and around Class B and Class C airspace, and enhanced navigation around special use airspace. VFR pilots should rely on appropriate and current aeronautical charts published specifically for visual navigation. If operating in a terminal area, pilots should take advantage of the terminal area chart available for the area, if published. The use of VFR waypoints does not relieve the pilot of any responsibility to comply with the operational requirements of 14 CFR Part 91. VFR waypoint names, for computer entry and flight plans, consist of 5 letters beginning with the letters VP and are retrievable from navigation databases. The VFR waypoint names are not intended to be pronounceable, and they are not for use in ATC communications. On VFR charts, a standalone VFR waypoint is portrayed using the same 4-point star symbol used for IFR waypoints. VFR waypoint collocated with a visual checkpoint on the chart is identified by a small magenta flag symbol. A VFR waypoint collocated with a visual checkpoint is pronounceable based on the name of the visual checkpoint and may be used for ATC communications. Each VFR waypoint name appears in parentheses adjacent to the geographic location on the chart. Latitude, longitude data for all established VFR waypoints may be found in the appropriate regional chart supplement US. When filing VFR flight plans, use the 5-letter identifier as a waypoint in the route of flight section if there is an intended course change at that point or if used to describe the planned route of flight. This VFR filing would be similar to VOR use in a route of flight. Pilots must use the VFR waypoints only when operating under VFR conditions. Any VFR waypoints intended for use during a flight should be loaded into the receiver while on the ground and prior to departure. Once airborne, pilots should avoid programming routes or VFR waypoint chains into their receivers. Pilots should be especially vigilant for other traffic while operating near VFR waypoints. The same effort to see and avoid other aircraft near VFR waypoints is necessary, as is the case when operating near VORs and NDBs. In fact, the increased accuracy of navigation through the use of GPS demands even greater vigilance, as there are fewer off-course deviations among different pilots and receivers. When operating near a VFR waypoint, use all available ATC services, even if outside a class of airspace where communications are required. Regardless of the class of airspace, monitor the available ATC frequency closely for information on other aircraft operating in the vicinity. It is also a good idea to turn on landing lights when operating near a VFR waypoint to make the aircraft more conspicuous to other pilots, especially when visibility is reduced. Lost procedures. Getting lost in flight is a potentially dangerous situation, especially when low on fuel. If a pilot becomes lost, there are some good common sense procedures to follow. If a town or city cannot be seen, the first thing to do is climb, being mindful of traffic and weather conditions. An increase in altitude increases radio and navigation reception range and also increases radar coverage. If flying near a town or city, it may be possible to read the name of the town on a water tower. If the aircraft has a navigational radio, such as a VOR or ADF receiver, it can be possible to determine position by plotting an azimuth from 2 or more navigational facilities. If GPS is installed, or a pilot has a portable aviation GPS on board, it can be used to determine the position and the location of the nearest airport. Communicate with any available facility using frequencies shown on the sectional chart. If contact is made with a controller, radar vectors may be offered. Other facilities may offer direction finding (DF) assistance. To use this procedure, the controller requests the pilot to hold down the transmit button for a few seconds and then release it. The controller may ask the pilot to change directions a few times and repeat the transmit procedure. This gives the controller enough information to plot the aircraft position and then give vectors to a suitable landing site. If the situation becomes threatening, transmit the situation on the emergency frequency 121.5 MHz and set the transponder to 7700. Most facilities, and even airliners, monitor the emergency frequency. Flight diversion. There may come a time when a pilot is not able to make it to the planned destination. This can be the result of unpredicted weather conditions, a system malfunction, or poor pre-flight planning. In any case, the pilot needs to be able to safely and efficiently divert to an alternate destination. Risk management procedures become a priority during any type of flight diversion and should be used by the pilot. For example, the hazards of inadvertent VFR into IMC involve a risk that the pilot can identify and assess and then mitigate through a pre-planned or in-flight diversion around hazardous weather. Before any cross-country flight, check the charts for airports or suitable landing areas along or near the route of flight. Also, check for navigational aids that can be used during a diversion. Risk management is explained in greater detail in Chapter 2, Aeronautical Decision-Making. Computing course, time, speed, and distance information in flight requires the same computations used during pre-flight planning. However, because of the limited flight deck space and because attention must be divided between flying the aircraft, making calculations, and scanning for other aircraft, take advantage of all possible shortcuts and rule of thumb computations. When in flight, it is rarely practical to actually plot a course on a sectional chart and mark checkpoints and distances. Furthermore, because an alternate airport is usually not very far from your original course, actual plotting is seldom necessary. The course to an alternate destination can be measured accurately with a protractor or plotter, but can also be measured with reasonable accuracy using a straightedge and the compass rose depicted around VOR stations. This approximation can be made on the basis of a radial from a nearby VOR or an airway that closely parallels the course to your alternate destination. However, Remember that the magnetic heading associated with a VOR radial or printed airway is outbound from the station. To find the course to the station, it may be necessary to determine the reciprocal of that heading. It is typically easier to navigate to an alternate airport that has a VOR or NDB facility on the field. After selecting the most appropriate alternate destination, approximate the magnetic course to the alternate using a compass rose or airway on the sectional chart. If time permits, try to start the diversion over a prominent ground feature. However, in an emergency, divert promptly toward your alternate destination. Attempting to complete all plotting, measuring, and computations involved before diverting to the alternate destination may only aggravate an actual emergency. Once established on course, note the time, and then use the winds aloft nearest to your diversion point to calculate a heading and GS. Once a GS has been calculated, determine a new arrival time and fuel consumption. Give priority to flying the aircraft while dividing attention between navigation and planning. When determining an altitude to use while diverting, consider cloud heights, winds, terrain, and radio reception. Chapter Summary. This chapter has discussed the fundamentals of VFR navigation. Beginning with an introduction to the charts that can be used for navigation to the more technically advanced concept of GPS, there is one aspect of navigation that remains the same. The pilot is responsible for proper planning and the execution of that planning to ensure a safe flight.